It's time to talk about systemic and alveolar gas exchange. We're doing the respiratory system, all right? Remember, the main job of the respiratory system is to exchange gases. We need to get oxygen into our body, then deliver it to the cells, then pick up the waste product of CO2 from the cells, and then get it out of our body. Let's look at how that's going to happen. This is such a great topic, by the way. Remember, our class is called Anatomy and Physiology. This is just an outstanding example of physiology. This is so beautiful. I love this example. You'll probably see it again later. So here in the tissues, remember, we've been making ATP. Here's the interstitial fluid. This is the fluid surrounding all the cells of your body. So inside the cells of your body, you're making ATP. Remember, oxygen and glucose make ATP with the byproducts of heat, water, and CO2. CO2 is the toxic byproduct of making ATP. Now remember, gases always move from high pressure to low pressure. So out here in the body, because lots of cells are dumping CO2 into the ISF, there's a lot of CO2. There's not nearly as much in the blood because eventually the blood gets rid of it. So partial pressure here is 46 millimeters of mercury. I didn't write that in because it's a small space on a small board. Here in the blood, partial pressure is 40 millimeters of mercury. So which way does CO2 go? CO2 goes from high pressure to low pressure. So CO2 will therefore enter the blood. All right? So we now have CO2 inside of a red blood cell. And of course it's going to mix with water because there's water. Half of your body is water. So what happens now when CO2 mixes with water? Here's where you don't even have to know any chemistry, you just have to be able to count letters, all right? So how many H's are there? There's 2 H's. How many C's are there? There's 1 C. How many O's are there? There's 1, 2, 3 O's. H2CO3. This is carbonic acid, all right? Carbonic acid is a weak acid, but like all acids, it dissociates in solution, which means it breaks apart into a hydrogen, which is the acid part, and the conjugate base, which is whatever is left over. So this is, by the way, facilitated by an enzyme called carbonic anhydrase, CAH. This reaction will take place no matter what, but it happens much more quickly in the presence of CAH. And, you know, in the body, we want to get the exchanges done quickly, so we have the enzyme to do that. So we're going to dissociate into a hydrogen ion, and what's left over? After we take one of the H's away from H2CO3, we're going to have HCO3. That's going to have a negative charge. That's the conjugate base. That's our old buddy, the bicarbonate ion, which we covered on the first day of class. And we're going to have a hydrogen, which has a positive charge, right? H plus HCO3 is H2CO3. It dissociates going this way. So what we're going to do at this point is, remember, we've got the bicarbonate ion is the principal buffer of the ECF. And this is the way most carbon dioxide travels in your blood. So what happens is the HCO3 gets kicked out. All right? It's now going to ride out here in the blood. So the HCO3 minus now travels in the blood, carrying carbon dioxide. Remember, we started with CO2. This is the way carbon dioxide is temporarily carried in your blood, in the form of the bicarbonate ion. Now the problem is we kicked a negative out, and we got to keep the positives and negatives balanced. That means we need to move a negative in. Well, this is blood, this is extracellular fluid. What is the most common anion of the ECF? Blood, ECF. What is the most common negatively charged ion of the ECF? We covered this on the first day of the semester. Do you remember what that is? I hope you do. That's chloride. So what we're going to do is we're going to take a chloride ion and we're going to move it into the blood, red blood cell, in order to balance the negatives. We kicked a negative out, we're going to then pull a negative in. All right? So what's going to happen at this point? Well, we kicked out the bicarbonate ion, so we've still got a hydrogen, all right? We've got a hydrogen ion, and then here we're in the tissues of the body, so this is blood that has been coming. This is oxygenated blood, arterial blood, so we're going to have HbO2. HbO2 is oxyhemoglobin. This is hemoglobin that's carrying oxygen for us, okay? Because it's just been coming from the lungs where it got the oxygen. So in this situation, the conditions are going to favor the hydrogen replacing the oxygen on the hemoglobin. So what we're going to create now is we're going to create deoxyhemoglobin, HHB. The hydrogen gets onto the HB is hemoglobin. Hydrogen gets onto the hemoglobin, kicks the oxygen off. So the hydrogen now it's HHB instead of HbO2. The hydrogen is now bound to the hemoglobin, and we are going to kick the oxygen off. All right? Well, let's take a look at the partial pressures. The partial pressure here in highly oxygenated blood is 104 millimeters of mercury. The partial pressure of oxygen out here in the tissue fluids is 40. So remember, gases always go from high pressure to low pressure. So what's the oxygen going to do? It's going to go this way. And by golly, look what we just did. We just picked up carbon dioxide, the waste product. We pulled that out of the interstitial fluid, and we pumped an oxygen into the interstitial fluid where it will diffuse through the ISF until it is taken up by a cell of your body. So we accomplished exactly what we hoped. We got rid of the waste product and we delivered oxygen to the tissues. Success! We're doing a good job so far, all right? Well, let's take a look then at what's going to happen now. So we've got the bicarbonate ion that we kicked out, all right? So the bicarbonate ion is going to travel, wrong marker. Bicarbonate ion is going to travel here, all right? It's going to travel through the blood until we get up here someplace, all right? So we have still the HCO3 minus. And the bicarbonate ion is now going to diffuse into the red blood cell, all right? So bicarbonate ion diffuses into the red blood cell. Let's take a look then at what we've got happening out here in the alveolar air. This is the air we just breathed in, okay? Just breathed all this in. So this air is really high in oxygen. So we've got oxygen out here, all right? We just breathed it in. Let's take a look. Here the partial pressure of oxygen is 1.59. Here, 159, sorry, not 1.59 for God's sakes, 159. And then the partial pressure of oxygen here in the blood is 40. See the same, 40 down here, 40 up here, it's the same. All right. So 159, 40, which way is it going to go? Gases always diffuse downhill, all right? They always go from high pressure to low pressure. So the oxygen is going to enter the red blood cell, all right? Oxygen comes right on in. So when oxygen comes right on in, what we're going to have here is we're going to have the oxygen and we've got the hemoglobin. So the hemoglobin, remember, the hemoglobin, this is blood that has traveled back now to the lungs, all right? It was out at the body, it's now traveling back to the lungs. So now we have, once again, a hemoglobin, HHB. This is hemoglobin that got rid of, all right? Remember, we ended down here with hemoglobin that had gotten rid of the oxygen and picked up a hydrogen. So here we have HHB again. Well, what's going to happen in this case? In this case, under these circumstances, the reaction is going to favor oxygen kicking the hydrogen off of the hemoglobin. So what's that going to create? That's going to create oxygen hemoglobin. Whoops, let's do it this way. HbO2, all right? This is oxyhemoglobin, all right? And remember, we then kicked off the hydrogen, so we have a hydrogen up here. Well, by golly, here comes a bicarbonate ion that has traveled all the way from the tissues back here into the lungs. So now we're going to take this hydrogen and we're going to add it to the HCO3 minus. All right? Now, remember, we had to balance the negatives down here. Well, we have to balance them again up here. So if we're going to pull a negative out of the fluid here, we've got to put a negative back in. I wonder what negative we could put back in. How about this chloride that's been riding all the way back to the lungs? So now we're going to take this chloride and we're going to kick it back out. We pulled it in at one point. Now we're kicking it back out again, okay? So now we're going to have a chloride back into the blood, into the extracellular fluid where we would expect to find it. What's going to happen then at this point? Well, once again, we've got our classic reaction here. So we're going to take H plus HCO3, all right? And remember, these reactions are occurring according to the proportions of the reactants, okay? Principle of Le Chatelier. So here we have the, in this case, the bicarbonate and the hydrogen. They are going to merge together. They're going to recombine and form our old buddy H2CO3. All right? And what's going to happen then at this point? Well, now we're going to continue going this way with the reaction, and we are going to end up with, we're going to break these apart. Remember, we started down here by putting them together to make the carbonic acid. Down here then, what we're going to end up doing is we are going to use carbonic anhydrase once again, and we're going to break apart the water and the CO2. So we're going to get some water, and we're going to get some CO2. All right? And let's look at the partial pressures. Partial pressure of CO2 here in the blood is 46. Partial pressure out here in atmospheric air is incredibly low, 0.04. So once again, which gases always go from high pressure to low. So which way is the gas going to go? It's going to go this way, all right? And we end up with CO2 out here. So look what we just did. Once we got it up into the lungs, just based on the partial pressures and based upon the components we've been carrying in the blood, we end up pulling oxygen into the blood out of the air you just inhaled, and we end up kicking carbon dioxide out into the alveolar air, the air in your lungs, where you're now going to breathe it out. So look at this. This is incredible. This is actual physiology, kids. We have now seen exactly how and why. When you breathe in air, the oxygen is going to go into your blood and the CO2 is going to go out. And when you get down into the tissues, the oxygen is going to leave the blood and the CO2 is going to go in. They don't even need traffic signals or a roundabout or anything like that. It's all partial pressures and about the proportions of the reactants, okay? That governs the whole thing. By the way, this little exchange over here, we call these the chloride shifts, all right? So, and I can remember which one is called which. The chloride shift, I'm not even going to try. One of these is called the chloride shift, and the other one is called the reverse chloride shift. And I can't remember which one is the normal way and which is the reverse way. So, as far as I'm concerned, it's chloride shift, and you don't have to say reverse chloride shift. But the chloride shift is where we exchange bicarbonate and chloride in order to balance the negatives in the blood and in the ECF and so on. So again, alveolar, this is what we often refer to as, this is alveolar gas exchange. So alveolar gas exchange. And then down here in the body we have what's often referred to as systemic gas exchange. And this is the whole job of the respiratory system. This is what it's all about. Getting the oxygen in and the CO2 out. And we've now seen exactly how it happens, okay? Text or email me with questions.